Welcome, and now we're moving on to our third lecture, which is on entropy, enthalpy, exergy, and exergy destruction. All trying to keep that being applied to fuel cell systems. So just as a reminder, this is from the last lecture. We're going to be using these equations a lot. They're the energy conservation and the entropy balance equations for open systems. And if it's a not steady state process, then what you have is the change in the internal energy inside of a control volume, which is your system. The change with respect to time is going to be equal to the flow rate in and out of enthalpy, which as you see, you multiply the flow rate times the molar enthalpy. And you can see here, because we've used a minus sign in front of the E, which is for exiting, values of N dot sub E are all going to be positive. And then we have the thermal energy entering being positive, right? So if it were to be negative, then it would be leaving. And then we have minus the amount of electrical and mechanical work that leaves the system. And here, if it's leaving the system, we define work to be positive. And the entropy balance equation is that the change in the entropy inside of that control volume as a function of time is equal to the entropy that enters or exits in flow of material. All right, so we've got flow times a molar entropy associated with each flow. And then, and this time, any thermal energy, if it comes in at some temperature T sub J, then the entropy associated coming into the system would be Q dot J over T sub J. And then, of course, what we have is any internal irreversibilities occurring inside the system. That's the last term there. So, first state property we're going to be looking at is entropy. This is a property of a substance, right? And it's either the entropy or the molar entropy if you're talking about per mole of something that's entering or exiting a control volume. So we're going to go through, we're going to look at 4 different examples. And in each example, what we're going to imagine is flow into a control volume is what's coming in on the left-hand side of these equations. And then what's exiting is what's going to be on the right side of these equations. Okay? And just as a reminder, if you haven't seen this before, but entropy is a monotonically increasing function with temperature. So if you go to 0 temperature, there's 0 entropy. And almost all materials are solids at 0 temperature. So as you increase temperature, your entropy of that substance is increasing mainly to the uncertainty in vibrations, and you could think of it as a lack of knowledge about which molecules are vibrating for a given amount of energy input into the system. And then what you see is a disconnect, you see a jump as it goes from a solid to liquid. And then once again, you increase the entropy of a substance, including a liquid, increases with temperature. And then you'll see another disconnect again. There's a jump as you go in the entropy of a substance as you go from a liquid to a gas. So we're going to look at these cases where the box is kept at a constant temperature and pressure, but we have a system that's flowing in with, let's say, first time is liquid water and it's leaving as a gas. Okay, so a couple of things we can say about this, right? We know that there's an increase in the entropy. All right, so if we look down at this equation down at the bottom, right? What I've done is I've taken the second law balance equation and rearranged it and put how much internal irreversibility is occurring, and that has to be greater than or equal to 0. So what we can say is that the the flow of Exergy exiting the system minus the flow of entropy entering the system minus the flow of entropy. Okay. The flow of entropy exiting the system minus the flow of entropy entering the system minus the flow of thermal energy divided by the temperature that it enters or exits has to be greater than 0. So as we go from liquid water to gaseous water, these terms, the net here is going to be positive. And then what it's saying is that this can happen as long as the heat transfer out of the system is basically at or greater than the temperature of boiling in this case. So if T is a really, really large number, higher than TB, which is the boiling point, then this reaction can go forward. If you're just on the, let's say, left of the temperature of boiling, so a little bit below it, what this equation will tell you is that that reaction is not spontaneous. It's spontaneous above TB, and it's not spontaneous below TB. Okay, so now we're going to go through another case, which would be calcium carbonate, which is also called limestone. That may go, so we're going to flow in calcium carbonate, and the question is, can we turn it into calcium oxide, which is called lime, and gaseous carbon dioxide. So once again, the flow of entropy into the system is going to be less than the flow of entropy out of the system. And the reason we can see this is we have two solids. Each solid is going to be fairly, at the same temperature. Their values of molar entropy are about the same. What we have now is a gas, carbon dioxide, and that's going to have a lot of entropy. So what we have here is that exiting the system, there's going to be a lot more entropy than entering the system. So what it will tell you is this reaction will go forward as long as the heat input into the system, Q, at some certain temperature, as long as that heat is coming in at a temperature above, we'll call it the temperature which we are releasing CO2. As long as it happens above some certain temperature, then that reaction can occur. And if you're below that temperature, then the reaction is not going to occur. So that's kind of what we saw in the last case with water. You have to be above a certain temperature of that heat that's coming into the system. Then we have another case. We have nitrogen and hydrogen making ammonia. You have one nitrogen, 3 molecules of hydrogen making 2 molecules of ammonia. So here we're going to have a net decrease in the entropy, meaning the flow rate of entropy into the system is greater than the flow rate out, because you have 4 molecules coming in and 4 gaseous molecules coming in and 2 leaving. So what this is telling you is that Q here, you could have this reaction occur if Q is negative and if T is at a if T is a small value, or Q in T, Q is going to have to be given based back on the first law balance. So that's going to be a given, and in this case, Q will be negative. Actually, is going to be exiting the system. So the question is, once again, what temperature? So what you'll find here is that the reaction can occur if you are below a certain temperature. So the formation of ammonia, as people know from either plant biology, you need to, or from the different chemical processes of making it, you can't go to too high of a temperature. This reaction needs actually a low temperature, and if you stay below that temperature, then this reaction can occur in what I'll call the forward direction. Right? If you get to too high of a temperature, the methane will not be forming from nitrogen and ammonia, nitrogen and hydrogen. Okay, this last one is the kind of the trick question. What happens when you have a mole of carbon monoxide and a mole of water vapor that could go into carbon dioxide and hydrogen? It's called the water gas shift, and it's one way you'll see in this class of how do we get hydrogen from various fossil fuel energy sources that may have release carbon monoxide, either from like coal or natural gas. There's going to be some carbon monoxide, so you could shift that over into carbon dioxide and hydrogen. So in this case, it's not clear. You can't just do it's not simple. You have to actually go and look up to figure out what the net entropy is here, because you got a biomolecular species and a trimolecular species going into trimolecular and a biomolecular. So it's not obvious. There is a very, very small entropy difference, and small compared to some of these other equations. But it's non-zero, so to actually figure out what's going on in this equation, you actually have to look up what the values of entropy are. And but this is a trick one. There is a very, very small difference for this fourth one. Okay, in this one, we're going to walk through some of the definitions of entropy. We're going to be starting off. Remember, capital S's are it's the entropy inside of a control volume, which is equal to the number of moles of a substance in the volume, in the control volume, times the universal gas constant, times the logarithm of the number of microstates. So from statistical mechanics, you can plug in what the number of microstates is, or how many the number of microstates are, and that's in the class notes, and you can put that in, and that's how we're getting from those first equations down to the rest of the equations here. And you can always divide the total entropy by the number of moles, and you get a molar entropy. And this is what we'll be using for substance flowing into or out of a system. So entropy is equal to the universal gas constant times the log of the number of microstates. And for most of what we'll be doing here, we're going to just, in this class, we're going to be okay with these equations here, starting with this S2 minus S1. The little hats, remember, for the molar. What we're doing here is if it's an ideal gas and there's a constant specific heat, if it's not saying that real gases are this way, but if you had a gas that was ideal, meaning it essentially has almost no volume and no intermolecular forces, i.e. it's a billiard ball, and its specific heat doesn't change with temperature, which is not real gases, but might be something close to hydrogen over temperature ranges that we're interested in. The change as you go from state 2 to state 1 is equal to the specific heat at constant volume times the logarithm of the temperature T2 over T1 plus the universal gas constant times the logarithm of V2 over V1. You can work in constant C sub P, in which case that same entropy change from state 2 to state 1 is equal to C sub P, the specific heat at constant pressure, times the logarithm of T2 over T1 minus the universal gas constant times the logarithm of P2 over P1. Okay, so now in these next equations, we're gonna take away one of the assumptions. In this case, we're not going to assume it's this constant specific heat. We're going to assume that the specific heat looks like a constant plus some linear correction term. And that linear correction term is beta. It tells you the slope of the constant specific heat as a function of temperature. So what you'll see here is you can correct this equation above, and it has an effect. So we're using the constant C sub P1. What it does is you have to correct around C sub P at 300 kelvins, and you still have that logarithm of T2 or T1, but you've essentially now added this linear term, beta times T2 minus T1. And you still have that minus R over log of P2 over P1. And if you have a mixture, right, so here we're going to take away another assumption. Now what you're flowing in isn't all, let's say, hydrogen. Maybe it's a mix of hydrogen and carbon monoxide and water vapor and carbon dioxide. Okay, but the entropy of the mixture between state 1 and state 2, that difference, is pretty simple. You just basically take the entropy associated, the molar entropy associated with each species, and multiply it by its molar fraction in the gas. So that's that chi sub I. It's its molar fraction. So if it's 50% hydrogen and 50% water vapor, that chi here is 0.5 and 0.5, and you just are basically waiting to get what the mixture is. Okay, here, so you have a general feeling. What I'm plotting here is the constant specific heat divided by the universal gas constant. That's a dimensionless number, and what you'll find is that it's actually a function for gases. It's a function of temperature. Hydrogen is one of those gases where, over what our range of interest, there's almost no change between 300 degrees Kelvin and 1,000 degrees Kelvin. So anytime you're dealing with hydrogen, you don't even need the linear correction. You can just treat hydrogen as having a constant specific heat. And in this case, what you see is the constant specific heat is equal to 3/2. And where that's coming down is the C sub V, in this case, would be 2.5. And the reason it's 2.5 is that each degree of freedom available to a system has associated with it a value of 1/2 in these units. So hydrogen has 3 degrees of translational freedom. You can move the molecule up, down, left, or right. So that's going to give you 1/2, right, or 3/2. Sorry, 1.5, which is 3/2. It's also going to have 2 degrees of rotational freedom. You can move it. It's symmetric bimolecular. It's going to have 2 rotational degrees. So that gives you 1 or 2/2. So you add 2/2 to 3/2 and get 5/2. So that's where, and then that's for C sub V, and if you remember, C sub P is over R is equal to C sub V over R plus 1. So that's why hydrogen is coming off at 3.5. You can see nitrogen and oxygen start off, and carbon monoxide start off at 3.5 at 300 degrees Kelvin, but then they increase. And the reason that they're increasing is that you're getting another degree of freedom that's starting to kick in, but it hasn't completely kicked in, and that's the vibrational. And that's the reason why these carbon monoxide, nitrogen, and hydrogen are not 3.5. They're actually starting to increase. And because this degree of freedom is not fully kicked in, but it's partially kicked in. Water vapor you see starts at 4, and that has to do with the fact that it actually starts off with 3 degrees rotational, it's not perfectly symmetric about a line. So we can have 3 degrees. So it starts off at 4 and then goes, so you can see, starts increasing from 4, and that's because of because of vibrational degrees of freedom that start kicking in. Carbon dioxide, once again, would be starting around 4, but it quickly has a lot of vibrational modes that are available, so that one you can see kicking in. And methane is the other one that it's starting around 4, and then once again you can see its degrees are kicking in. Actually, CO2 being symmetric, like about a line, like hydrogen and oxygen, actually should be starting around 3.5. But you can see it looks like some vibrational motions have already started kicking in, which is why it does not start like hydrogen, oxygen, or carbon monoxide around 3.5. And the other thing is, you can see hydrogen here, it's some of its rotational degrees haven't even kicked in yet, which is why temperatures below 300, it's less than 3.5 in these units. Okay, so now we're going to move on to the next of the state properties. Here we're going to look at molar enthalpy, which is equal to the molar internal energy plus the pressure times its molar volume, or its volume divided by the number of moles, which you can think of as an inverse density. So for an ideal gas, the molar enthalpy between state 2 and state 1, so the change in the molar enthalpy between state 2 and state 1 is equal to the integral of the specific heat at constant pressure times the change in temperature between state 1 and state 2. So as we saw, C sub P may not be a constant with temperature, so this is why we need the integral. So if we do the linear approximation, what you find is that the change in the molar enthalpy, it's going to be some kind of constant times the difference in temperature, and then we're going to also have this term right here where it goes like difference squared, T2 squared minus T1 squared, times that linear correction. So we're going to be using that a lot throughout this course, and we can put those back into that first law. That's where we're going to be needing it, is we're going to be needing to know the enthalpy, the molar flow enthalpy. Okay, we're going to very briefly talk about real gases. This is just so that you know when you can make the ideal gas approximation. And so I'm going to go through this fairly quickly. There's a lot more of this information in the class notes in chapters 2 and 3. So, okay, the reasons why real gases don't always follow the ideal gas law. And the ideal gas law being that PV is equal to nRT. Okay, so real molecules actually have a certain size, and real molecules have intermolecular forces of attraction or repulsion to other molecules. Which what we're saying is they're not perfect billiard balls with no volume. And when you start including the size and the intermolecular forces, you can't use the ideal gas law. You'll have to either use some kind of approximation, like van der Waals gas, or you can go into what's called the viral expansions. So most of the gases we're going to study can be treated as ideal gases, especially for almost anything we're doing with solid oxide fuel cells, which are going to be happening at high temperatures. Okay, the times that we can't are going to be for when there's liquid water or water vapor near or around its critical point of water, which is 647 Kelvin, 374 degrees C. So this is going to be for PEM fuel cells. Anytime you're treating systems with liquid water, you can't treat liquid water or even steam near its when it's in equilibrium with liquid water. as an ideal gas. And the other times there's going to be corrections would be if you have a lot of, let's say we're storing either natural gas or hydrogen in storage tanks on a vehicle. You'll find that there's slight corrections that you need to make, largely taking into the volume and some little bit of taking into the intermolecular forces. So there's a couple ways you can do. There's like viral expansions. You can either expand with respect to density or with respect to pressure. And just note, Z is non-dimensional. It's what you take as P over the density times RT. For an ideal gas, it's equal to 1, but for real gases, it's not equal to 1. It can either be greater or less than 1. It's always going to be greater than 0, though. So you can you can go out to higher orders either in density or pressure, and just note that when you go out in density, the unit each term in the viral expansion has it's B sub 2V, or if you're expanding with respect to pressure, you'll see it as B sub 2P. And for van der Waals gases that have finite size and pairwise molecular interactions, what you'll find is B sub 2V is equal to RT times B sub 2P. So there's a relationship between the first order correction, if you do it either in density or pressure, and it's equal to B minus A over RT. B tells you something about the volume, and A tells you something about the intellectual intermolecular forces. And if you're interested, you can check out any Wikipedia page on van der Waals gases to show you where B and A come from. So here we're going to look at, I've written down some of the critical pressures and temperatures just so you get a feel for when we can make ideal gas approximations. So this first one, let's look at nitrogen and oxygen. You can see the critical temperature is in the orders of 100, around, let's say 100 to 150 degrees Kelvin. When you're above the critical temperature by at least 1 or 2, you can and as long as you're nowhere near the critical pressure, you can treat such a gas as an ideal gas. So nitrogen and oxygen, you can treat as ideal gases until you get to the point in which maybe you're doing any type of cryogenics or something like that for, let's say, oxygen separation. When you do oxygen separation cryogenically, then yes, you would have to take and count as a real gas. But for anything we're doing, you can treat nitrogen and oxygen as ideal gases. Okay, so water vapor, you can see the critical temperature is really high compared to any other gas. And so unless you're at temperatures of like 8 to 1,000 Kelvin, which you'd be at, let's say, for a fuel cell, or when you're combusting, right? In a combustor, you can treat water vapor as an ideal gas. But water vapor in PEM fuel cells, you can't treat as an ideal gas. Carbon dioxide is an interesting one. Its critical temperature is right around room temperature. So it really depends on the pressure of carbon dioxide. And I mean, once you start going well above room temperature, you don't have to worry about treating non-ideal effects. Or if you're at low pressure, you can see the critical pressure is around 73. So as long as you're well below 73 atmospheres, you'll be fine with carbon dioxide. What is interesting is that oftentimes in power plants that are trying to capture and sequester CO2, CO2 is what in the state that's called supercritical. It's where you're near the critical temperature and pressure, and that's because that's pretty much the pressure you need to overcome the geologic reservoir. So you may be pressurizing CO2 to 120 or 150 atmospheres, so you're above its critical pressure, and you're going to be sitting around room temperature, so you're sitting right around this critical temperature. So it's actually in a state called a supercritical fluid. And then So the next thing we're going to look at is hydrogen. You can see hydrogen, as long as you're not anywhere near cryogenic temperatures, you can almost treat it as a ideal gas. Though its critical pressure is not too high. So when you start storing it, though, you can hit cases where you may be storing it at maybe 120 atmospheres or something like that. So you're actually sitting at very high pressures compared to its critical pressure, and there's some small non-ideal effects that come into play. Carbon monoxide is going to look just like nitrogen, oxygen. It's very similar to them. Methane is going to be someplace in between, like carbon dioxide and nitrogen. It's only if you store it at some really high pressures and low temperatures that you'll have to take any account of non-ideal effects. We're now going to quickly go through, just look at real gases and their fugacity as a function of what's called the reduced pressure and the reduced temperature. And there's a nice graph where if you know the reduced temperature and pressure of a fluid, you can then plot it on the graph to the right, and you can figure out what its fugacity coefficient is. Fugacity coefficient is the ratio between the fugacity and the pressure. So fugacity coefficient is dimensionless, and fugacity has units the same as pressure. It could be atmospheres or bars or megapascal. And so if you want to correct, one of the things you have to do is if you want to correct for real gases is in the definition of the entropy change between state 2 and state 1, right? We had, there's going to be a term, which is an integral of c sub p over t dt. Instead of using minus r times the logarithm of p2 over p1, what you do is you just use f2 over f1. So if you know the pressure, you just need to know what the fugacity coefficient is. So you go to a figure like the one over here, and what's nice is that there's a very simple equation that goes between for this f and p, or the fugacity coefficient, and the ratio f of p is equal to e to the z minus 1. So you can expand that out, and what you get is it's equal to z plus, and then higher order terms in terms of z minus 1, either squared or cubed, or even higher terms. So when you're near z is equal to 1, right, when you're near the ideal gas, the fugacity coefficient is just equal to z. And so as you saw before, z was equal to 1 plus, and then you expanded that out in terms of like the viral expansion. Either if you did the viral expansion with the pressure, you'd have a 1 plus b sub 2p times p, and then you're going to have a 3 sub b sub 3p times p squared, and higher order terms. So, but when you're near z is equal to 1, you just have to take into account the very small change. So when you're near z is equal to 1, it's pretty much a linear equation for how do you get the fugacity coefficient. And as you can see, when you put that into a logarithm, you don't really get all that much of an effect. It's really when you start going away from z, and that's that can happen for a number of different reasons. So what we have here is reduced pressure that's equal to the pressure divided by the critical pressure. And the other variable on this graph is the reduced temperature, which is the temperature divided by the critical temperature. So you can see for a lot of substances where you're near the critical temperature and pressure, you can start getting major deviations where z is no longer near 1. And in those cases, you can see the fugacity coefficient is in most cases less than 1. And what, in some ways, what that's saying is that for a given pressure, if this coefficient out in front of the, say, F2 is less than it would be if it were P2, there's less entropy in state 2 than there would be if it was an ideal gas. That's one way of thinking about it. There's less entropy as you go below at z is equal to 1, or at coefficient is equal to 1. And the other case would be you can go up. It's rare, but there are some cases where you can have z greater than 1. That does happen sometimes with compressed hydrogen, in which you're at a very, very, very high value of P sub r, reduced pressure, and you're at a fairly high temperature, critical temperature. And you can actually get values, but once again, they're not very large. Maybe you go to z is equal to 1.1 or 1.05. It's not going to have a very large effect on the definition of entropy change between state 2 and state 1. Okay, so now we're going to be moving into the exergy. We've seen this definition before, but I'm going to state it again. Because entropy is a property of a substance and in its environment. It's not a state function, as entropy and enthalpy were. It's a property of a substance with respect to its environment. So exergy is defined as the amount of work obtainable when a system is brought from its initial state to a state of thermodynamic equilibrium with the common substances of the natural environment by a means of a process that were to generate no internal entropy. So it's the maximum amount of work that you can get from bringing a system from some non-equilibrium state to some equilibrium state, and if you could do it perfectly reversibly. That's what the definition of exergy is. So it's a property of a substance and its environment, and it tells you how much work could be generated if we lived in a world with no irreversibility. Now, the trick, of course, is that if we lived in a world with no irreversibility, we'd all be at the equilibrium state. So it's this kind of ideal exergy kind of, it's what we could hope for but can't ever really get. It's what we could hope for is amount of work, but we just can't get that amount, because any real process is going to have internal generation of entropy. So here's some more just definitions and a diagram to kind of give us a more feel for what's going on here, a better feel for what's going on. So we got a system in complete equilibrium within its environment has no entropy. So that's one definition. Has no exergy. If you're in complete equilibrium, you have no exergy. The exergy of a system increases the more it deviates from the environmental pressure, temperature, voltage, and chemical composition. So when you're close to the equilibrium state of the environment, no exergy, you start getting higher pressures, temperatures, voltages, or chemical composition, and your exergy is going to start increasing. So exergy cannot be destroyed. Exergy can be destroyed, it cannot be created. Right? The only way you could technically create entropy is if you change your definition of the environment. Right? But once you fix what you define as your environment, the exergy cannot be created, it can only decrease. Which is what I was saying here. The exergy is a function of the pressure, the temperature, and the chemical composition of the environment. So here we got this diagram, right? Imagine we have a system on the right at some high temperature, pressure, voltage, or chemical potential. And on the left, low temperature or pressure or voltage or chemical potential. So as we go from the right side to the left side, the amount of energy is going to stay exactly the same. So in this case, let's treat this as kind of a piece of steel that separates a high temperature heat bath, to a low temperature heat bath, or heat sink of some sort. So as energy goes from one side, it's exactly equal to the amount of energy that comes. So the amount of energy coming from the right is equal to how much enters the left side. The exergy is high on the high temperature side, and what's actually, when it gets over to the other side, what you're left with is maybe much smaller. So exergy is decreasing, but what's increasing is the entropy associated with that thermal energy. The entropy for the same amount of energy is low on the right side and then high on the right side. Sorry, low on the right side, high on the left side. So here we're going to be talking about the flow exergy of a single substance, and this is what we're going to be using when we eventually derive a exergy balance equation. So the molar flow exergy, so the inputs into this are going to be the temperature and pressure of the material as it enters or exits the control volume, and then once again we're going to need P naught and T naught, the temperature and pressure defined for the environment itself, not the control volume, but of the environment, outside environment. So we've got this term H minus H naught, and we've got a minus T times S minus S naught. Here there's hats on all the H's and S's to mean this is a molar, meaning it's a per mole term. So if it's a if there's a constant specific heat, right, we can use the C sub P times T minus T naught. If it isn't, we just have to make that correction as we saw before for H minus H, as we defined before, H2 minus H1, right? So H being the temperature, define it at the temperature of the substance as it enters or if it's exiting the system, and then T naught being the reference environment. So we may need to have a linear correction term to the enthalpy. And for the entropy, we've got some kind of S minus S naught. And we may have to correct that too if it's C sub P is not a constant. And the other thing we may have to do is, if it's a non-ideal gas, we may have to correct the pressure by putting in a frigacity. And so we can combine those two and we get the molar exergy flow rate. So we get some kind of, using those approximations of ideal and constant specific heat, this is what we get. We get a C sub P times T minus T naught minus T naught times the quantity, C sub P times the logarithm of T over T naught minus R times the logarithm of P over P naught. Any times a naught, those are for the reference environment. What's nice is that the flow exergy for a mixture is going to be really simple, just like in the other cases. You take the exergy of each of the molar exergy of each of the substances, and you multiply it by chi sub I, which is its mole fraction. So if it's half hydrogen, half water vapor, then you use 0.5 and 0.5 for chi sub H2 and chi sub H2O. So for things aren't all that difficult for a mixture, you just need to know what the composition of the gases are in the mixture. Okay, so there's going to be an exergy balance equation, and you can get this from the first and second laws of thermodynamics. That's going to be a problem in homework number 1. So just as we saw with the second law of thermodynamics, we can write a balance equation. It's not a conservation equation, but it is a balance equation. So when you work it out for a steady state system, down the steady state system is going to be the very, very bottom equation. If it's not steady state, you have the equation above. So let me go through the terms above. The change in the exergy inside of the control volume as a function of time, at the rate of change with time, is equal to the flow rate of exergy into and out of the system. So here we're defining into n dot sub I would be flow into the system, and it's positive. If it's exiting, then n dot sub I would be negative. So you multiply that flow rate times the molar exergy of substances, materials coming into or out of the system. And then we've got a term for thermal energy entering or exiting the system at, if it enters or exits at temperature T sub K. And then we've got terms for work. So you minus the amount of work. And you can see there's a term you have to subtract off if the control volume is changing, if its volume is changing with time. Luckily, we're not going to be looking at those type of systems. Our fuel cell systems, the volume of a fuel cell doesn't change with time, which is nice. And then there's going to be a term minus T naught times sigma dot irreversible. So you arrange that, and what you find is the amount of electrical work leaving the system is equal to the you can think of the exergy entering minus exergy leaving, plus the term for any heat that's entering or exiting, and minus T naught times sigma dot irreversible. So this is the main thing we're going to be finding, is that the amount of work is going to decrease as the irreversibility increases. T naught times sigma dot irreversibility is the destruction. You can think of it as the destruction of exergy. The higher that sigma dot irreversible is for a given, for the other given terms, right, on the flow of exergy into and out of a system, the less work you're able to get out of the system. And for our we're not going to be working that much with mechanical work or any kind of piston type of system. So W dot is normally just W dot electrical. That's the other approximation that's gone into this equation. So the way we got from the first equation to the second one was if we assume steady state. Okay, so we have a couple simple cases. We could put a dashed line around the Earth just outside at which the atmosphere, the pressure of the atmosphere goes to 0. And if we did that, we could do an exergy balance. We could use that equation that we just saw from the last equation, from the last slide. There's no work entering or exiting the Earth, right? The only thing we have is we have some thermal energy entering and thermal energy exiting. Enters as mostly as visible, some UV photons, and it's going to be exiting in the microwave. So we could calculate, if we wanted, the amount of irreversibility occurring on the Earth if we knew the amount of Q dot and the temperature associated with the Q dot. So if we assume all the Q dot is leaving at the temperature of the Earth, T is equal to T naught in that case, right? So that term actually would drop out. So the amount of irreversibility going on would be the temperature of photons from the sun, which is about 6,000 degrees, minus 300 divided by 6,000, right? So that's essentially 1. So the amount of irreversibility going on the Earth is pretty close to the flux of photons that are coming from the sun divided by T naught, the temperature of the Earth. We could do another, if we had a Carnot, let's say for a Carnot cycle, we could figure out if we had a Carnot cycle and somehow we could do things reversibly, I'm not saying that we could actually do it in real life, but if you could somehow do it, if you could do it reversibly, and you had a control cycle, there's no change in the overall control. You have a lot of terms that drop out, and what you get is basically the work is equal to T minus T naught over T times the temperature at which thermal energy enters or exits the system. So this is essentially how you get Carnot efficiency, is from this kind of Exergy balance. And for a fuel cell, you can do a similar type. Here we're going to assume steady state. Some terms drop out, and so for the fuel cell system, the amount of work you can get out of it depends on the Exergy flowing in and out, if there's any heat into or out of the system. And notice how if there were PEM fuel cell operated at the temperature of the environment, T is equal to T naught, that heat term would drop out. So if you had a PEM fuel cell at room temperature, the work is going to be equal to the Exergy entering minus Exergy exiting minus the irreversibility that's occurring in the fuel cell times T naught. That term is T naught times sigma dot irreversible.